So we're going to continue with chapter 7 and look at section 7.7, which is factoring special products. So first thing that we're going to see here is what's called the difference of squares. Okay, and we saw this actually might look familiar to you when we were distributing or we were multiplying polynomials together. We were kind of going in the opposite direction. We said to you at that point that this is an important pattern for you to recognize. Well, now we're going to be factoring. So now, instead of given x plus 3 times x minus 3, you're going to be given something like this, x squared minus 9. And you have to be able to recognize that that is a special case. That's the difference of squares. When we have the difference of squares, it's always going to factor to the square root of a and the square root of c. And then we have a plus and a minus here. Okay? In addition, for some of you, it might be easiest to think of this as saying, okay, let me just rewrite it with a b term there. So if I say x squared and I just put a 0x in the middle, because 0 times anything is 0, I can do that. And then minus 9 at the end, you can think to yourself, what numbers do I need to multiply to 9 or negative 9 that are going to add to 0? And that would just be 3 and negative 3. So there's two ways to think of this pattern. So let's take a look at the first example here, where we have x squared minus 25. And if we want to write this, this is the difference of squares. We want to say, okay, my first term here is x squared. If I take the square root of x squared, I'm going to get x. My c term is 25. If I take the square root of 25, I'm going to get 5. Now, this only works, this pattern, when both your a and your c terms are perfect squares. So this is going to factor to x minus 5 times x plus 5. Now, if you're confused by that, you can just think to yourself, okay, let me rewrite this as x squared plus 0x minus 25, and then come up with values that are going to multiply to negative 25 and add to 0, which is obviously 5 and negative 5. Okay? So there's my answer there. Now, same idea here. Notice that 4 is a perfect square. 1 is a perfect square. It's the difference of perfect squares here. So if I think to myself, okay, take the square root of 4z squared. That's going to be 2z, because the square root of 4 is 2, and the square root of z squared is z. And the square root of 1 is just equal to 1. So this is going to factor to 2z plus 1 times 2z minus 1. Doesn't matter the order that you write your two factors in. Now, if you're somebody who's confused by this, feel free to write this as 4z squared plus 0z minus 1. And then you can use your factoring when a is not equal to 1 technique. So if you want to factor by using grouping, you can factor by grouping. If you want to factor by using the slide technique, you can use the slide technique or guess and check. But remember, you're going to start by multiplying your a times your c term and then go from there. Doesn't matter, however you want to think about it. Okay, if you can recognize these difference of square patterns, though, that's your best or your easiest bet. We're not going to worry about this particular example here. We can skip this. I'm sure you're all thrilled about that. Okay, we'll look at the try these in class, particularly 1 through 4. Now, another type of case that you'll see is what we have here, which is called a perfect square trinomial. Once again, we saw this when we had one of our special cases before, okay? And we saw something like this where we had x plus 3, and then we were going in the opposite direction, and we were foiling out to get x squared plus 6x plus 9. Now we're doing the opposite thing. But again, you don't need to memorize these patterns that you see here. If you want to memorize them, go for it. Okay, but you don't need to memorize them. You could just factor in the same way that we were factoring before. But if you do recognize that both your first term and your last term are perfect squares, that's your clue that this is a perfect square trinomial. So for example, on this particular problem, letter A, it's very easy to just factor this normally, right? If we think about things that are going to multiply to 16 and add to 8, obviously it's 4 and 4. So I'm going to get n plus 4 times n plus 4. But if I notice here that n squared is a perfect square, that equals 4. If I take, nope, sorry, that's not what I wanted. If I take the square root of n squared, right, I get n. And if I take the square root of 16, I get 4. And then 2 times 4n is equal to my middle term of 8n. that checks all the boxes of a perfect square trinomial, which means it's just going to end up being n plus 4 squared as my answer. Either of these are correct. Just know that those are equivalent. Now, in letter B, if I wanted to, I could use the same factoring technique that we saw in the previous lesson when a isn't equal to 1. So I could go ahead, I could multiply 4 times 9, I could get 36. What multiplies to 36 and adds to negative 12, negative 6 and 6, and go from there. Or I see that this is a perfect square, and this is a perfect square, and I say to myself, okay, 4x squared, take the square root of that. You're going to get 2x. Take the square root of positive 9, and you're going to get 3. And if I multiply 2 times 2 times 3, or 2 times 2x rather, times 3, I'm going to get 12x, which is my middle term. Notice that on this particular problem, your middle term is negative. Here it was positive. Hence why I have a plus. Everything was plus here. Here, everything's going to be minus. So my final answer is going to be 2x minus 3 times 2x minus 3. Or a better way to write that, 2x minus 3 quantity squared. Now, you could, like I said, have gone the other route by multiplying 4 times 9, getting 36, and using it the same way that we factored previously. Example 4 is a tricky one, okay? But it is a perfect square trinomial because x squared is a perfect square and 1/9 is a perfect square. So I say to myself, okay, x squared, take the square root of x squared, and that's going to be x. 1/9, if I take the square root of that, take the square root of the numerator and the denominator is equal to 1/3. So while this seems initially challenging, it's not as difficult as it seems. And you can think to yourself, what numbers do I have to multiply to 1/9 and add to 2/3? So this is going to be x plus 1/3 times x plus 1/3, or x plus 1/3 quantity squared. These are both equal to 0. Now, if I'm asked to solve this, which I am, all I'm going to do is I'm going to set, and there's only the same thing that I have to set, x plus 1/3 equal to 0. Subtract the 1/3, and you'll get your solution of x is equal to negative 1/3. So these are your special cases. Okay, we'll look at some more examples in class. If you want to write them down, you certainly can. But they're just special cases. And again, like I said, we'll look at the word problem and the special cases in class. But we're just factoring some special versions of what we've been doing. See you then.